Okay. Fluorine reacts with water to form gaseous hydrogen, fluoride, and oxygen. The first part is to write a balanced equation. So here we've got fluorine, fluorine gas plus liquid water, giving us HF gas plus O2. I'm just going to migrate this a bit. Try to migrate it without it fighting with me too much. And leave some space for balancing. Okay. So to balance this now, so we've got one hydrogen on this side and two on this side, so I'm going to plunk a 2 there. But we need 2 oxygens actually, so erase that 2. We need 2 oxygens, so we need a 2 there. That makes 4 hydrogens, so we need a 4 here. And then now we have 4 fluorines, so that gets a 2 there. And then now everything looks balanced. Okay. And then use tabulated data to determine the free energy change for the reaction. Okay, so fluorine gas is in its standard state, so our delta G of formation is 0. Oxygen gas is also in its standard, so that's delta GF is 0. For water, liquid water, what I found is delta GF is minus 228.6 kilojoules per mole. And for HF, I found that delta GF is negative 275.4. So our free energy change for the reaction is the sum of our products minus the sum of our reactants put this in a way that's a little bit easier to know what I'm talking about. Delta G of our products minus the delta G's of our reactants. Where each of these need to be multiplied by their appropriate coefficients. So that in this case, for our products, we have 4 times negative 275.4 kilojoules per mole, plus 0 for oxygen. And then on our reactant side, so we have minus, and on our reactant side we have 0 for fluorine and 2 times minus 228.6 kilojoules per mole for water. If we run this on our calculator here, then we get negative 644.4 kilojoules per mole. Okay. And so the next part of the question says, so there's our free energy for a reaction. Now the next part of the question asks to calculate the enthalpy change using tabulated data. So again, delta H F for F2 is 0. Delta HF for O2 is 0. What I found was delta HF of water is negative 241.8. And delta HF of HF is negative 273.3. And so now we're good. So we can calculate delta H for our reaction, and it's the same steps as for the free energy change. So it's the sum of our delta HFs for our products minus our delta HF for our reactants. And we're going to put in our appropriate coefficients with this. So then, looking at our equation again, right, our products are HF and O2, and our reactants are water and fluorine. And we've got a 4 on our HF, so that'll be, just moving this down a bit, so that'll be 4 times minus 273.3 for HF, plus 0 for oxygen, and then minus our reactants. So that's 0 for fluorine gas, and 2 times minus 241.8 for our water. So that's our HF, and that's our water there. And if we work this all through, then we get minus 609.6 kilojoules per mole. Okay, and the last part of the question asks, determine how much heat flows and in what direction when we have a mass of fluorine gas of 34.5 grams. Okay, so to answer this, we need to solve for the moles of fluorine that this corresponds to. So we need our molar mass. So our molar mass of fluorine is 2 times 18.998403 grams per mole, which is equal to 37.996806. And so our moles of fluorine are just equal to our mass over our molar mass. So 34.5 grams over 37.996806, which is 0.90797 moles. Okay, so there's our number of moles of fluorine. And then we can use our delta H to compute our heat flow, as delta H is equal to our heat. But one thing we need to consider is what a delta H of minus 609.6 kilojoules per mole means in this case, or what we mean by a mole. So the way I like to think about this, even though this isn't a proper unit, is mole of reaction. So this is per mole of reaction, or this is per run through our equation. So a mole of reaction is kind of one path through the reaction. So there's 2 moles of fluorine per mole of the reaction, 2 moles of water per mole of the reaction, 4 moles of HF per mole of the reaction, and 1 mole of oxygen per mole of the reaction. Okay? So that's kind of the way I like to think about it, because that's really what the mole is that we saw for in our delta H here. So to get our total heat flow, it would actually be Q over N. To get our total heat flow here, it'll be delta H times N, which is minus 609.6 kilojoules per mole of our reaction times, and so this is the moles of fluorine, so we need to multiply this by our conversion here, right? So there's per mole of reaction, there's 2 moles of fluorine, and then we're multiplying by the number of moles of fluorine that we just solved for. And so these would all cancel. And again, mole reaction and mole fluorine are not real units, but I'm just tagging that stuff there just as placeholders so we can keep track of everything. And so running through these factors on our calculator, we would get minus 276.75 kilojoules. And that's also what direction. So minus means that it's leaving, so it's on the product side. So the heat flows, flows toward products, or it leaves the system. Okay. All right. So running through all of our solution here, right from the top. So there's our balanced equation, which looks good. The delta G's of formation that they found are a little different from mine, but that's okay. It depends what table you use. And so these values might differ depending on who measured them, basically. But that's fine. Everything should come out roughly similar, as long as we run through all the equations the same. So 4 times your delta G for HF, and then 2 times that for water. And because of the differences, our values come out a little different, but that's okay. And then for our delta HF, our delta H is for our delta H's of formation are also a little different, of course. quite different, actually, especially in the water case, but well. The point is, again, that the equation is done properly, and it looks like it is. And so again, our values are going to come out quite different because our delta H's information that we had looked up were quite different, but that's okay. Solving for the number of moles, so that looks good. And then to get our heat, we just rearrange this expression. So we multiply our delta H by N, but we need to take into account that there's 2 moles of fluorine per mole of the reaction. And so that's where the division by 2 comes in. And so it's a different value because our tabulated values were different, but everything was done correctly. And so that looks good. And actually, I'm going to stop that here and say that's going to be the end of my session. I hope everyone enjoyed this. If you did, please subscribe to the OneClass channel. If you want to add questions, please follow the links below the video. This has been Jeff Krause for OneClass.